Well, hello. Sorry I'm not going to be with you, but this is a lecture on section 1.3. It's actually 4 videos. They're all short. And this is to replace section 1.3 in the book, which I don't care much for. You'll find in the book that, on the D2L site, that there are some exercises. There again, the presentation style, step-by-step exercises, which will show you how to work with Framework 1, which is the networks. We're going to have essentially 3 types of applications we return to over and over in this semester. We're going to look at internet search engines. These are giant linear algebra-based machines. We're going to look at scientific models, especially age and stage-based models, which are very useful in particular when they reach some type of equilibrium. And we're going to look at data representations, especially in physics. Now, some of you may know physics uses vectors, often 3-dimensional vectors, but linear algebra in physics goes far beyond the use of simple 3-dimensional vectors. There are going to be some common themes on these applications. One of these themes is going to be networks. Our applications will be models of networks, and then a lot of them will be Markov chains. Andrei Markov introduced this idea based on graphs or networks, also known as transition diagrams, and Andrei Kolmogorov in the 1950s made them a very powerful tool in science and technology. So what we're going to think when we see one of our applications is we'll have some collection of states, which will be vertices or nodes, and they'll be connected by edges with probabilities of going from one state to another. So here we have some states 1, 2, and 3, and we'll have edges, and the numbers on the edges are probabilities of going from one state to another, and of course all the probabilities for departing must add up to 1. If there's no probability of going from one state to another, then we just don't draw that edge. Now, we'll see other edges with numbers on them later on. Another common theme is going to be transitions. So transitions is when there's a before and it changes to an after. So Markov chains are actually models of transitions. And in particular, a transition is a linear combination of the values of the states before the transition. So notice that word linear combination. We'll see this quite a bit. We'll look at web bots, crawlers, spiders, Autobots. They have different names. These are automated web page users, and they move from page to page, and the number of bots after a transition is the sum of all the bots, a linear combination of those who came from before transition. The third thing we'll see is equilibria. Now, not all physical processes reach an equilibrium. However, some do, and when they do reach an equilibrium, then what that means is essentially the system stays the same over time. Now, there may be changes within the system, robots running around from one web page to another, but the number at any given place at any given time is pretty much the same. Likewise, we may see a population that becomes stable, like squirrels in a section of a woodland, and this is not because there are no longer deaths and births, but because the number of deaths and births tend to equal each other out. Here's an example. So a series of web bots ran around the web pages that ended with ETSU.edu. Eventually, about the same number of web bots were on a given page at any given time. The hotter colors indicate higher numbers of web bots on a page, so that's the orange and the reds and the yellows. And equilibrium means that the hot pages are always hot and the cold pages are always not. So the hottest page is goldlink.etsu.edu. Catalog web pages are over here in this section of the graph. D2L pages are here. This hot spot in the middle is mainly what's linked to by D2L. And the library is this little node up here that you see. So we're going to see common themes. Physical, computer, social, and biological systems in which there are interrelationships modeled by a network, Individuals transition from the network, through the network from state to state, and after some period of time, the number of individuals in a given state doesn't change between transitions. So we're at equilibrium. The outgoing balances the incoming. So we'll see that if you take equilibrium plus transition plus multiple states, you get systems of linear equations. A variable for each state, transitions modeled by linear combinations, and equilibrium, which implies equations. Now you're ready to go on to the next video. So that's the next one on this YouTube site, and it's about framework number 1.